welcome to the Deep Dive. You've sent us a stack of sources detailing just these incredible cosmic breakthroughs happening right now, all centered on the James Webb Space Telescope, the JWST, and the phenomenal data it's delivered in its first 4 years.
Today we are strapping in for a look at how this machine is actively rewriting the entire cosmic story. We're synthesizing data from NASA, the European Space Agency, and, a whole host of recent astrophysical reports from late 2025.
And our mission is clear: to uncover the most surprising, paradigm-shifting findings. We're going from stellar nurseries right in our own galactic neighborhood all the way out to the mysterious edge of the universe, what astronomers call the cosmic dawn.
Right. And the sheer volume and quality of the high-resolution data pouring in is it's challenging foundational cosmological models at an astonishing pace. What we're seeing is a universe that is far more dynamic, more mature, and more complex far earlier in its history than anyone ever really predicted.
So this isn't just incremental science.
No, this is a true intellectual revolution.
Okay, let's unpack this, and we'll start close to home with an observation that provided a really spectacular and I think appropriately timed holiday image: the cosmic Christmas tree.
This is a truly spectacular piece of deep space portraiture. Formally, it's known as NGC 2264. It's a textbook example of massive star formation, and the JWST's infrared eyes gave us a completely unprecedented look into its complex interior.
And when we say massive, we really mean it. This is an extremely active stellar nursery located about 2,700 light-years away in the faint constellation Monoceros, or the Unicorn. But what really puts the scale in perspective for you is that this whole region spans nearly 80 light-years across.
It's a huge, bustling laboratory, and when you look at it from Earth, that 80 light-year sprawl creates an apparent width of about 1.5 degrees.
Which, for context, is what?
That's roughly the size of 3 full moons lined up side by side in your night sky. It's just immense.
And the structural components are what give it that Christmas tree shape. At the core, you've got the Christmas tree cluster, a kind of triangular pattern of bright, young stars. It's visually anchored near the center by S Monocerotis, which is a massive variable star that actually fluctuates in brightness.
And these young, intense stars are actively shaping their environment. So at the top of that cluster is the really dramatic Cone Nebula. It's this towering structure of dense gas and dust.
Right, it looks like a pillar.
It does, but it's actually being fiercely sculpted and eroded by the intense radiation and stellar winds just blasting out from the newborn stars beneath it.
And then sprawling out below that, you have the Fox Fir Nebula, which is, it's aptly named for its tangled, textured appearance. It's in these regions that the physics of light truly come alive with these incredible colors.
Exactly. The characteristic deep red glow we see is from what are called emission nebulae. This happens when these young stars ionize the surrounding hydrogen gas, causing it to emit light in the red spectrum. And conversely, the soft blue regions, which are really prominent around S Monocerotis, those are reflection nebulae. Dust clouds simply reflecting the blue light of the nearby hot young stars.
What's crucial here is why this local view matters so much, especially when our main goal is looking at the far universe. You're basically observing, in real time, how vast amounts of raw material get converted into newborn stars.
And then how the intense energy from those stars disperses the very clouds from which they formed. It's a complete dynamic laboratory for stellar birth and evolution. And the sheer energy output in NGC 2264 naturally transitions us to the instrument that can see past all that, the James Webb Space Telescope.
Launched on Christmas Day 2021, the JWST is a $10 billion collaboration between NASA, the ESA, and the Canadian Space Agency. Its location is almost as impressive as the telescope itself. It sits 930,000 miles from Earth at a stable orbital spot called a Lagrange point.
Yeah, and that Lagrange point isn't just about stability. It's all about temperature. See, JWST operates in the infrared spectrum. If it were closer to Earth, the heat signature from our own planet would completely drown out the faint, billion-year-old signals it's trying to capture.
It's that sensitive.
It's that sensitive. That distant point allows the massive sun shield to passively cool the telescope down to near absolute zero. It achieves the sort of thermal silence it needs to see infrared light.
The infrared advantage is the absolute game changer, and it functions in 2 fundamental ways. The first is pretty intuitive: penetrating dust.
Right. Visible light is stopped dead by these thick, opaque clouds of cosmic dust. But infrared light, which has a much longer wavelength, it just slices right through, allowing JWST to peer into the very heart of stellar nurseries like the one we just discussed, and deep into the previously hidden nuclei of galaxies.
And the second reason is why JWST is so often called a time machine, seeing back in time via redshift.
Think of it like a siren on an ambulance passing you. As it approaches, the sound waves are compressed, so the pitch sounds higher.
Right, the blue shift for light.
Exactly. But as it speeds away, the sound waves are stretched, making the pitch lower. And in the cosmos, well, everything is speeding away from us because the universe is expanding.
So the light from the earliest galaxies has been traveling for so long that the expansion of space itself has stretched its wavelength.
Precisely. It stretches visible light all the way into the long infrared wavelengths. By capturing that faint, stretched infrared signal, JWST has proven it can see 98% of the way back to the Big Bang, observing structures that formed as early as 300 million years after.
And the data from that early time is already challenging the standard model, not just about the universe as a whole, but about our place in it. It's revealing that our own solar system is something of an interplanetary oddball.
That's right. The telescope is constantly finding these common classes of planets elsewhere that are just conspicuously absent from our own neighborhood. Types like mini-Neptunes and super-Earths. These intermediate planet types are clearly widespread, which suggests that, maybe the arrangement of our local worlds is the exception, not the rule.
Here's where it gets really interesting, though. The data JWST has poured back over the last year is forcing scientists to rethink the entire timeline of cosmic evolution, specifically with black holes and just the sheer pace at which massive structures can form.
This is probably the most profound shock from the cosmic dawn. Our previous models suggested it would take billions of years for gas to slowly accrete and form these massive structures. Yet JWST has found shockingly bright galaxies containing supermassive black holes or SMBHs that just shouldn't exist so early.
And we have two incredible examples confirmed in 2025. The oldest and most distant SMBH was found in a galaxy called Kuiper's LRD Z9. It's seen just 500 million years after the Big Bang, and this black hole already weighed about 300 million solar masses.
That is the paradox. For a black hole to get to 300 million solar masses in only 500 million years, it must have been consuming matter at or even above the theoretical maximum rate, something called the Eddington limit.
Wait, I have to stop you there. If the mechanism is so mathematically constrained, are we absolutely sure these aren't just, statistical flukes? Does this fundamentally break the theory? Or is it just a massive tweak?
Well, it creates a massive tension. It means our canonical theories of black hole seeding and growth, the idea that they started small and grew slowly, are either incomplete or perhaps entirely wrong for the early universe. And there's another example. The black hole in CANUCS LRD Z8.6, seen 570 million years post-Big Bang, was growing far faster than we would expect.
So it's a pattern.
It confirms this is a pattern. It seems to be a rule of the early cosmos, not a fluke.
That speed and scale are honestly hard to grasp. But perhaps the most mind-boggling discovery of the last year is the confirmed first sighting of a runaway supermassive black hole.
This is absolutely phenomenal. We're talking about a 10 million solar mass titan rocketing through space at a blistering 2.2 million miles per hour. This black hole was likely ejected during a violent three-way galactic merger.
And what's so counterintuitive about this is that it's not purely destructive. It's dragging this enormous plume of gas behind it, a 200,000 light-year-long tail, where new stars are actively forming because of the shockwaves.
It's an engine of creation flying through space. The team leader, Peter Van Dockum, he summed it up perfectly, saying, "It boggles the mind. We always pictured black holes as these gravity-driven consumers, yet here's one actively triggering star formation on a galactic scale simply by moving."
And the dramatic black hole dynamics aren't just limited to the early universe. Closer to home, 2025 was a big year for observing Sagittarius A star, the supermassive black hole at the center of our own Milky Way, which was once famously thought of as quiet.
SGR A star is anything but quiet. JWST detected these highly energetic flares from it in the mid-infrared range for the very first time, filling a critical gap in our understanding of how often and how violently it bursts. At the same time, the ALMA telescope discovered what they dubbed space tornadoes, violent streams of gas raging around our own galactic center.
Which just proves that the extreme cosmic violence we see at the edge of the universe is still relevant today. We saw that flare, J2245 plus 3743, 10 billion light years away, release energy equivalent to 10 trillion suns.
And that energy doesn't just disappear. Look at the cosmic burp from the SSBH in galaxy NGC 3783. It was seen ejecting a jet of material at 134 million miles per hour. That's about 20% of the speed of light. Studying these powerful outflows is key to understanding a concept called feedback, how black hole activity actually controls and limits the growth of its own host galaxy over cosmic time.
Speaking of growth, let's pivot from cosmic violence to how this data is refining the existing rules of structure formation, starting with the importance of dwarf galaxies.
Dwarf galaxies are vital because they're considered our local analogs for the first galaxies of the universe. When we talk about first galaxies, they were characteristically gas-rich and low in something called metallicity.
And just for clarity for our listener, what do astronomers mean by metallicity?
It's basically everything on the periodic table heavier than hydrogen and helium. In the early universe, almost nothing else existed. Stars needed time to fuse those heavier elements, the metals in their cores, and then spread them through supernovae. So dwarf galaxies, which have a lower concentration of these heavy elements, give us a window into what those first metal-poor building blocks looked like.
And JWST gave us this detailed view of the interacting dwarf galaxies NGC 4490 and NGC 4485, located about 24 million light-years away.
Right, and this specific pair is the closest known dwarf-dwarf system where we can clearly resolve individual stars. Observing their collision and merger gives astronomers an empirical template, a real-life, high-resolution map of how early cosmic structures grew through collisions billions of years ago. We can use it to refine our simulations of cosmic evolution.
That we have the ancient supernova puzzle. JWST observed the death of a massive star, designated SN and GRB 250314a, seen when the universe was only 730 million years old. This was the first direct look at a stellar explosion from that infancy era.
And the surprise was a real challenge to theory. It was surprisingly similar in brightness and spectral properties to modern local supernovae, like one called SN 1998BW.
So the prevailing theory that these low metallicity stars would explode in a dramatically different way because of their different chemical makeup, that might be wrong.
It creates a new puzzle. It suggests that the core physics of massive star death, the collapse mechanism that produces the explosion, might be far more consistent across cosmic history, regardless of how metal-poor the environment was. This uniformity is a major conceptual shift.
Finally, let's look at this fascinating search for dark matter, which used archival data from Hubble to constrain the possibilities for the elusive stuff that makes up 85% of the universe's mass.
This research focused on searching for a theoretical dark matter particle known as the axion. Researchers used Hubble data to analyze the cooling rates of white dwarfs in the globular cluster 47 Tucana.
White dwarfs are essentially the dense, cooling cores of dead stars, like embers slowly fading out. It's a brilliant way to test particle physics because those cores are so incredibly dense.
The hypothesis was very clever. If axions existed, they would be produced by electrons inside those extremely dense white dwarfs. These axions would then fly out of the star, robbing it of energy and causing it to cool faster than standard physics predicts. You'd essentially have an extra cooling mechanism at work.
And the result?
To define it.
No. The analysis found no evidence of this axion cooling. Now, this doesn't rule out the axion entirely, but it places new, extremely stringent constraints on the particle's properties, its mass, and how strongly it interacts with electrons. This result really narrows the search parameters for the next generation of dedicated dark matter experiments.
So what does this all mean? The JWST's first 4 years have confirmed a dynamic, complex, and surprisingly mature early universe, compelling a massive reevaluation of our models for how fast structures form and the violence that drives it. Absolutely. The discoveries from black holes growing impossibly fast just 500 million years post-Big Bang to a runaway titan creating new stars while traveling at 2.2 million miles per hour, they aren't just finding new answers, they're exposing tensions in our current understanding and forcing us to question basic assumptions about our cosmic origins.
Indeed. The universe we thought we knew is actively being rewritten in real time. And that brings us to our final provocative thought for you to chew on. The JWST is expected to operate well into the 2040s, and future observatories like the Nancy Grace Roman Telescope are being developed specifically to tackle the questions about dark matter and dark energy that Webb is bringing into focus. If the telescope has already challenged fundamental scientific assumptions in its first 4 years, what entirely new foundational truths about our cosmic origins might it reveal over the next 2 decades?